Oh, okay, here we go with kind of our third video. And this is POD, actually not 9.5, but rather 9.4, which you'll be working on together. And basically it asks you to summarize a bunch of tests and strategies. And so, well, man, let's see. We've got lots of them. One, we need to check whether the limit as n approaches infinity of a sub n equals 0, because if it does not equal 0, then that implies that the series doesn't converge or diverges. We also want to think about, is it geometric? Okay, if it's geometric, we can apply that. We have the integral test. We have, is it a p-series? We have direct comparison. We have limit comparison. We have ratio test. We have the alternating series test. And we know that if the absolute value of something converges, then this converges as well. I think that might be it. We also have talked briefly maybe about conditionally convergent versus absolutely convergent. So just to remind you that conditionally means that this converges, but this does not. And this is conditionally, right? It depends on the oscillation to converge, versus if they both converge, then it is absolutely. Means that it absolutely convergent. So absolutely versus conditionally convergent is something that applies to alternating series and something you might want to think about. So just kind of want to have these in front of you, right? Just because that's your toolbox. All right, so here are some problems, and we've already done quite a few, but we're going to do some more and try and figure out which test to use here. I see a factorial. I think ratio test. Will it work? I don't know, but I think it probably should. I also think factorials grow really, really fast, so I'm guessing this thing is probably going to diverge. So let's see. The limit as n approaches infinity of n factorial divided by n plus 1 squared times the reciprocal of this, n squared over n minus 1 factorial. That is simply the limit as n approaches infinity of, well, all of these terms are going to divide, except for the n, so that's actually going to be n cubed over, and here we're going to end up with n squared plus 2n plus 1, and oh my goodness, that actually goes towards infinity. That means as n gets large, each successive term is way larger than the previous. That's bad. So we're adding up things that are getting bigger and bigger. And this tells us, since infinity is clearly greater than 1, right, that this series diverges by the ratio test. Okay, let's try number 3. E to the n. What? Come on now. The limit as n approaches infinity of e to the n does not equal 0. That sequence doesn't approach 0. We're adding up infinitely many infinities. Diverges. Boom, done. That was the easiest problem of all time. Cool. All right, moving on. 1 over n squared times tangent of 1 over n. Good night. Well, that doesn't look fun. What do we think? Ratio test? Limit comparison with 1 over n squared? Direct comparison? Look, what happens to tangent of 1 over n? as n approaches infinity, this goes to 0, and so tangent of 0 is 0. Interesting. Tangent, I mean, this thing is like basically less than 1 over n squared. So maybe we could use direct comparison. Let's think about this for a second. Can we show that this thing is less than 1 over n squared? Look, tangent of 1 over n. What if that was equal to 1? Because if that were equal to 1, then this would be equal to 1 over n squared. Now, if that's true, then 1 over n is equal to the arctangent of 1. And so 1 over n is equal to pi fourths. And so 4 is equal to n pi. And so 4 over pi is equal to n. Now that is between 1 and 2. So let's let n be greater than or equal to 2. Then I'm going to claim that 1 over n squared tangent of 1 over n is actually less than 1 over n squared. Right, because from 2 to infinity, the only thing tangent is doing is going closer and closer to 0. So it's just going to be less than 1. It's going to be between 1 and 0. Hooray! So by direct comparison, and by the way, 0 is less than this too. By direct comparison then, this series converges. Interesting. I wonder if there's another way to do that. Is there another way? Question mark? Did I mess up? I don't think so. I think that was kind of interesting. Cool. Okay, what do we have? Well, we've got 4 more problems. Not too many. 7 minutes in here. 5n over 2n squared. You don't need me to do that problem. I mean, come on. This thing behaves basically like 1 over n, which diverges. So how about you just use limit comparison? Use limit comparison with 1 over n. You'll have good success with that. All right, this one looks interesting. Negative 1 to the n minus 1 times 2 to the n over n squared. What? I don't even think that thing approaches 0. What if we just used L'Hopital's rule to show that the limit of that sequence doesn't approach 0, right? 2 to the n is definitely bigger than n squared. Check this out. The limit as n approaches infinity of negative 1 to the n minus 1 times 2 to the n divided by n squared is equal to, taking the derivative of the top and the bottom, is equal to, well, this is going to become, oh man, I don't want to do this, n minus 1. No, it's not. No, it's not. It's going to become negative 1. Oh, what is the derivative of this? Negative 1 to the n minus 1. Oh, wait a second. Now I'm really messed up. I can't take the derivative of negative 1 to the n minus 1 because I'll have a natural log of a negative. Frustration. You know what? It doesn't actually matter if this part is in here, right? Because if this doesn't approach 0, then making it oscillate, it still doesn't approach 0. So 2 to the n divided by n squared. All right, and that is the limit as n approaches infinity of 2 to the n ln 2 divided by 2n. Still infinity over infinity. That's the limit as n approaches infinity of 2 to the n times ln 2 all squared over 2, which is infinity. Okay, so the limit of this sequence does not equal 0. The limit as n approaches infinity of negative 1 to the n minus 1, 2 to the n over n squared oscillates between negative infinity and infinity, which is bad. Thus, the series diverges. Okay, sequence diverges. series diverges. Cool. All right, finally, sine of n squared over n squared. Oh my goodness, I mean, come on. This thing definitely converges. Compare it with 1 over n squared. You know, I mean, basically, like, 0 is less than sine of n squared over n squared. Absolute value is less than 1 over n squared. Less than or equal to. Less than or equal to. So, boom, direct comparison. Continue. Direct comparison. Continue. Okay, and how about here? N plus 2 over n squared minus 1. Oh, get out of town. Use a limit comparison if you want, but, you know, you can figure that out. That's just 1 over n. Limit compare that thing with 1 over n. Show that it diverges. It definitely diverges. And let's leave it at that. All right, I hope you're feeling pretty good about sequences and series.